Ice ages are long periods when the Earth cools, and large ice sheets cover a significant portion of the Earth's surface. What causes the cooling of the Earth? An ice age is not solely caused by one factor, but rather a combination of factors that contribute to the cooling of the Earth. Also, the cause of the ice age was different over time. Throughout the history of planet Earth, there have been 5 distinct ice ages. Scientists have identified the key factors contributing to these planets cooling during these periods. The first factor is Earth's orbit and solar radiation. The second is the reduction of greenhouse gases such as carbon and methane. The third is the thermohaline circulation. Volcanic eruptions can also have short-term effects because they block sunlight, but there may be other factors that still need to be clarified. This episode introduces the quaternary-related thermohaline circulation, which began 2.7 million years ago. Thermohaline circulation, or THC, is a part of the large-scale ocean circulation driven by global density gradients caused by surface heat and freshwater fluxes. The water in these circuits transports both energy in the form of heat and mass, dissolved solids and gases, around the globe. As such, the state of the circulation has a significant impact on the climate of the Earth. First, let's look at the Antarctic Circumpolar Current. The region around latitude 60 south is the only part of the Earth where the ocean can flow around the world without land obstruction. The water surrounding Antarctica flows clockwise, both on the surface and deep below. The map displays the flow of the ocean currents in 3 layers. The map shows the current surface water flow between 0 and 600 meters below sea level. It is the white line. This water circulates between the Drake Strait and the Tasman Sea. Some surface water flowing around Antarctica merges with the Benguela Current in southwest Africa and flows northward. On the other hand, the warm seawater passing through the Pacific Equator passes through the Indian Ocean and flows into Antarctic Circumpolar Current. Another ocean current that circulates Antarctica is the middle thermohaline layer water, which flows between 700 and 1200 meters depths. This is Antarctic Intermediate Water, or AAIW. In Antarctica, the third is the deep thermohaline layer of water flowing between 3,000 and 4,000 meters. This is Antarctic Bottom Water, or AABW. Antarctica has low solar irradiance. This causes the waters around Antarctica to cool. As it cools, the density of the seawater increases, making it heavier. When it becomes heavy, the seawater descends vertically. AAIW descends to a depth of 1,200 meters, and AABW descends to 4,000 meters. AAIW is relatively saline water mass that forms almost everywhere between 50 degrees south and 60 degrees south. Typically, temperature values for AAIW are 3 to 7 degrees Celsius. Antarctic bottom water, or AABW, has a temperature range of -0.8 to 2 degrees Celsius, or 35 degrees Fahrenheit, and forms in the Weddell and Ross Seas. The amount of water masses is 10 SV, or sphere drup. Sphere drup is the amount of water flowing at 100 cubic meters per second. In other words, in this case of AABW, 10 water masses of 100 cubic meters descends at a depth of 4,000 meters per second. The amount is unimaginably staggering. When was the Antarctic Circumpolar Current created? It is related to the plate tectonics. About 34 million years ago, the concentration of carbon dioxide in the atmosphere suddenly dropped, and the Earth cooled. The cause of the decrease in carbon dioxide is unknown, but scientists estimate that volcanic eruptions and meteorite impacts caused it. This period coincides with the Eocene-Oligocene transition, the mass extinction of marine and aquatic organisms. It also coincides with the opening of the Tasman Sea and Drake Strait. The opening of the 2 seas created the Antarctic Circumpolar Current, and Antarctica was covered with an ice sheet. From this point on, the Cenozoic glaciation begins. Before that, Antarctica had a forested subtropical climate. From now on, we'll follow the flow of the Antarctic Circumpolar Current. On the screen, purple is Antarctica bottom water flowing down 4,000 meters. Cyan is Antarctic Intermediate Water, and white is surface water. First, let's look at the flow towards the Atlantic Ocean. The bottom water that descends from the Weddell Sea and the surface current that circulated Antarctica flowed towards the Atlantic Ocean. Conversely, the intermediate water enters from the Atlantic Ocean and joins the Antarctic Circumpolar Current. The reason why the Antarctic circumpolar current flows clockwise is because of the Earth's rotation. Surface water enters from the Indian Ocean but flows directly into the Atlantic Ocean after joining surface water from the Antarctic circumpolar current. On the other hand, you'll see that the intermediate water flows westwards from the Southern Ocean. Just look at the Pacific Ocean. Bottom water descending from the Ross Sea flows towards the Pacific Ocean. On the other hand, intermediate water flows into Antarctica from the Pacific Ocean, and intermediate water flows out into the Pacific Ocean. Now, let's move slowly to the Atlantic Ocean, keeping in mind the flow of the Antarctic circumpolar current in the Southern Ocean. Antarctic bottom water from the Weddell Sea begins to rise when it reaches the vicinity of the equator slowly, turns into intermediate water, and changes direction about 20 degrees north latitude. This water flows along the eastern sea of South America back to the South Pole and joins the Antarctic circumpolar current. The Antarctic surface water, which entered the southern tip of Africa, flows from the equator to the coast of South America. And this water flows again to the Gulf of Mexico and becomes the Gulf Stream to the North Atlantic Ocean. These currents play an invaluable role in the Earth's climate. The graph on the screen shows that the radiant energy is much higher in the high latitudes, and the opposite occurs in the low latitudes. If left alone, the lower latitudes would get hotter and the higher latitudes get colder, but that doesn't happen. The reason is that this imbalance is resolved as some of the energy entering the low latitudes regions is redistributed to the high latitude region. It is the flow of seawater that plays this role. The ocean does not move as fast as the atmosphere, but it has a heat capacity of more than 1,000 times greater than the atmosphere. Among them, deep currents transport a tremendous amount of energy. It flows slowly, but the energy flow is staggering because it has so much volume. Let's look at another graph of the amount of energy movement in the north-south direction and latitude. The dark part is the amount of movement taken by the sea. In the high latitude regions of the North Atlantic, where the energy transfer is large, the Gulf Stream carries energy northward from the ocean's surface layer. At the same time, the deep water transport energy southward. The energy transport to the Gulf Stream is enormous, as surface waters that have crossed the equator are heated and are turned into warm water. The amount of energy the Gulf Stream carries is equal to all 27,000 power plants in the UK. Let's compare the average annual temperatures of cities at similar latitudes with London in the UK. London's average yearly temperature is around 11.7 degrees Celsius, while at the lower latitude, Chicago is more like about 11.3 degrees Celsius. To the east, Ulaanbaatar, Mongolia is also at a lower latitude but much colder than London. London has a lot of fog because the warm air evaporates from the Gulf Stream and the cold air from the North Atlantic meet the cools quickly. The heat released by the Gulf Stream continues to warm Europe and keeps the planet from cooling. As the warm surface waters that pass through the equator evaporate, their salinity increases. The Atlantic Ocean is the sea with the highest salinity. The on-screen map shows the salinity of the sea. The yellower the sea, the higher the salinity. And the darker the purple, the lower the salinity. You can confirm that the salinity has decreased due to the fresh water flowing down from the estuary area of the large river. In the Atlantic Ocean, the waters above the Sahara are the saltiest. In the case of the polar regions, salinity decreases in summer because the glaciers and sea ice melt. The salinity increases again in winter. The Gulf Stream was 500 times larger than the Amazon River. It flows along the coast of the United States, passes the coast of Iceland, and goes north to the Norwegian Sea. When it reaches the relatively salty oceans north of Iceland, it is cooled significantly to become dense enough to sink into the deep sea, forming North Atlantic deep water. There are two places where North Atlantic deep water, or NADW, is formed. One such place is the Greenland Sea. The water mass, which has become heavy due to high salinity at low temperatures, falls like a giant water drop to a depth of 2,500 meters. Another North Atlantic deep water source is the Labrador Sea between Labrador and Greenland. 80% is made in the Greenland Sea and 20% in the Labrador Sea. Adding these two is 15 million cubic meters, or 15 sverdrups. This is 5 sverdrups more than the Antarctic bottom water. When converted into a total amount for 1 year, it is 500,000 cubic kilometers. Since the North Atlantic deep water is 2 kilometers thick, it can be said that the spreading area in 1 year is 500 kilometers in all directions. These two deep waters flow in a submerged state in the Atlantic Ocean and slowly crosses the equator to reach the Antarctic Ocean. When passing through the Weddell Sea and the Ross Sea at the edge of Antarctica, the chemical composition is slightly changed while stony with other deep waters rich in salt. Wallace Smith Broker, a former professor of Columbia University's Lamont Doherty Earth Observatory, called this great ocean circulation the conveyor belt, and argued for the importance of climate-changing mechanisms. It takes about 1,000 years for one water mass to flow all over the great ocean conveyor belt, like the slow heartbeat of the world's climate. The sources of deep water in the ocean are North Atlantic deep water, which forms in the north, and Antarctic bottom water, which forms in the south. The balance between these two water masses governs the global climate. The cause of the Ice Age cycle found through Antarctic ice core analysis was revealed by Milankovitch. According to the Milankovitch theory, the climate change starts slowly and ends slowly. The Milankovitch effect combines several sinusoids with different periods, which does not explain rapid climate change. The clue lies in the on-off model that Broker insisted on. The conveyor belt theory is that the climate changes rapidly when the deep water flow conveyor belt stops or weakens. The current status of the conveyor belt is on, but if the flow of deep water stops and turns off, it becomes an ice age. In the off state, deep water formation in the North Atlantic Ocean stops, and the origin of deep water worldwide changes to Antarctica. It also stopped the supply of large amounts of heat energy from the Gulf Stream, which was moving to the northern part of the North Atlantic. What will happen as a result? If the heat supply is cut off, Europe and North America will be much colder than they are now. The water temperatures of the Gulf Stream flowing into the Greenland Sea, where deep water is currently forming, is about 10 degrees Celsius. But when it sinks to the depths, it drops to 2 degrees Celsius. 8 degrees of heat energy escapes into the atmosphere. This number corresponds to the 1/4 of the amount of solar radiation received in this area. The IPCC, or Intergovernmental Panel on Climate Change report published so far, explains the on-off of the conveyor belt as an essential mechanism that influences the climate. The Hollywood movie The Day After Tomorrow, released in 2004, was produced with hints of Broker's theory. Then, how the hell can this on-off switch be changed? The answer is simple and clear. It can be done by lowering seawater's salinity, that is, reducing the density near Greenland, where North Atlantic deep water is formed. You can rise the water temperature or reduce the salinity to reduce the cold water's density. However, to reduce the weight of 1 cubic meter of seawater by 0.001 grams, the water temperature must be raised by 10 degrees. In contrast, since you only need to drop the salinity by 1 unit, reducing the salinity is much simpler than raising the water temperature. An event caused this phenomenon in the North Atlantic during the last Ice Age. This must have been formed 19,000 to 7,000 before the present, when the massive Laurentide and Finniss-Candian ice sheets melted and flooded the North Atlantic with large amounts of ice melt. In particular, after the last glacial maximum ended, the Earth warmed up until 12,900 years ago, and then the world suddenly returned to the Ice Age for 1,200 years. This period is called the Younger Dryas. Melting water from the Laurentide ice sheet suddenly flowed into the North Atlantic Ocean, lowering its salinity. This caused the Earth to cool. Another example is the event that happened a long time ago. 6 million years ago, gradual changes in crustal structure blocked the Strait of Gibraltar, temporarily separating the Atlantic Ocean from the Mediterranean Sea. During this isolation, the Mediterranean Sea was flooded several times, and the thickness of the vast deposited salt reached a whopping 3 kilometers. This event, in which about 6% of the salt dissolved in the world's oceans was dissolved and removed, is called the Messinian Salinity Crisis. 5.5 million years ago, the Mediterranean was utterly isolated from the sea and turned into a salt desert. This period almost coincided with the time the world entered the Ice Age. These two incidents will be introduced by producing another video. Then, will deep water form in the North Pacific? As you can see on the screen, the surface water of the North Pacific is cool enough now, but it has about 1 unit less salinity than the Atlantic Ocean. The water temperature dropped to negative 1.9 degrees Celsius, the freezing temperature of seawater, but not enough to sink deep into the ocean. Formed in the Ross Sea, the Antarctic bottom waters head north into the Pacific Ocean and changes direction at the equator in around 30 degrees north latitude. As it moves south, its properties change to intermediate water, and it joins with the Antarctic Circumpolar Current. Meanwhile, while intermediate water circulated around Antarctica goes north along the west coast of South America and becomes surface water when heated at the equator. This surface water crosses the Pacific Ocean from near the equator to Halmahera Island in eastern Indonesia. It passes through the Indian Ocean and joins the Antarctic Circumpolar Current at the southern tip of Africa, and some head north into the Atlantic Ocean.